Hi Methods friends, how you going? It's me, Ben again, back again for another chapter of probability, and I've got great news. I've got a maths joke for you. Everybody loves a good maths joke. So there's a function going on, and it's a function for functions. All of your favorite functions are there. Sine, cos, and tan hanging out in their little clique as usual. The polynomials are out on the dance floor having a great time. 1 on x is there, chatting away to root x. Root x says to him, gosh, you exaggerate. You're being so hyperbolic. Another bonus joke for you. But over in the corner of the room, e to the x is by himself, really lonely, sitting there by himself. So x squared feels a bit sorry for him. X squared goes over to e to the x and he says to e to the x, why don't you integrate? And e to the x says, what difference would that make? That's pretty good, right? Right? You don't get it? Well, I'll explain it at the end. And if you still don't like it, then I don't know what to tell you. That's all my maths jokes. I'm out. So let's get on with the chapter. So this lesson's called Continuous Random Variables and Probability Distributions. We are taking everything we know about probability distributions in the discrete context, and we are branching out to continuous random variables. I hope you get a lot out of this chapter. It's my last one, so I'll try to make it really good for you. Okay, so a few things we're looking at here. We're going to look at what is a continuous random variable as opposed to a discrete one. We're going to look at what the probability density function looks like, and we're going to look at how we use those to calculate probabilities. So let's go. Okay, so what is a continuous random variable? We looked at sample spaces and we've looked at outcomes. We've looked at discrete random variables, and we talked about if all of the outcomes in our sample space is a countable list, then that would be a discrete random variable. But what if it's not countable? And in fact, what if the values from our sample space could be any real number, or any real number across an interval? So that would be a continuous random variable. And a better way to think of it is it's something that we would measure. For example, if I flip a coin in the air and I time how long it takes to hit the ground, well, then it could be any amount of time that we could possibly measure. So it probably wouldn't take more than, say, 5-6 seconds, but I could measure that really, really accurately, and it could be anything between, say, 0 and 6 seconds. It could be 3.9921 seconds, 3.99238 seconds. So there's an infinite number of decimal places that we could go to when we're measuring, which is what usually makes up our continuous random variable. So a couple of other examples, we could look at how long in hours you spend asleep in one day. I hope this isn't you studying. If it's you, Travis, wake up, please. If your name is Travis, you're probably really freaking out right now. Hi, Travis. Or it could be the temperature of a cup of coffee. Now, the temperature of a cup of coffee, technically, that random variable could be anything from negative infinity to positive infinity, because of course we can have negative temperatures. Now, I doubt there's going to be a cup of coffee that's negative 100 degrees Celsius, but the point is that our distribution could take any infinite number of values, and that makes it a continuous random variable. So easy to just think of it between discrete and continuous. Like I said back in that chapter, something you can count versus something that you can measure. So continuous random variables will be things like height, weight, sound, decibels, temperature, anything that you would measure. Okay, I'm not going to give you 1,000 examples. You'll see some as we go through the chapter. Now, one interesting thing here is that means that technically, because we can measure our continuous random variable more and more and more accurately, it doesn't actually make sense to look at the probability that x equals one given value. And in fact, we say that the probability that x is equal to something is 0, because it can't ever be exactly that value. So what I mean by that is, let's say the temperature of our cup of coffee, it could be 32 degrees. But if I measure it more accurately, it could be 32.134 or 32.134, 216 or 9, 2. I'm not going to keep going. But so the probability that the temperature is exactly 32 is actually 0, because it can never be exactly 32, because there's an infinite number of values that it can be. So it doesn't make sense to say that x is equal to 32. What we would do instead is I'd say, what's the probability that the temperature is between 31 and 33 degrees? What's the probability that it's more than 30 degrees? And so on and so on. And that's what we'll be looking at. Okay, so like I said, it'll make more sense when we get onto some examples, and I'll come back to this later as well. So I've got a question for you, first of all. So constructing a probability density function. So what are we talking about here? So this is how we're going to model our probability distribution. Now you'll remember our probability distributions when we were looking at discrete random variables, they looked something like that. So we looked at, well, our variable could take the values 0, 1, 2, or 3, and the probability of that happening was 0.1, 0.2, 0.6, and then 0.1 or something like that. Now with continuous, I can't do that because my continuous random variable could be anything from, say, 0 to 3 and everything in between. So I can't put an infinite number of values into a table. It doesn't make sense. So what I actually do is I end up modeling it with a function. Now let's look at an example. So let's say our random variable is how long Travis sleeps in one day. Hi, Travis. So here's a histogram. So I might gather a bunch of data about this particular gentleman and how much he sleeps, and I might turn it into a frequency table. So that's 4, 5, 6, all the way up to 18 hours and how many times it was observed. Now, if I do that for a really large sample and I measure that more and more accurately, what I can end up with is a curve. So I'm going to show you that curve now. So that would be a function, and the area under the curve is what I use for probability. So it could be that if I was just using some data and it was discrete, I would look at, say, the number of times he slept 15 hours in a day, and I'd divide that by how many observations. But a continuous random variable where it could be anything between 0 and, say, 24 hours and measuring really accurately, then what I end up is with a curve, okay? And that curve would have a rule associated with it, a function, okay? And then the probability is actually the area under the curve. So let's say I wanted to work out the probability that Travis is going to sleep between 10 and 15 hours. Then I'd find the area under the curve. And how do we find the area under the curve? We use integration. So this whole chapter, the first half of this chapter is all actually using a lot of revision from the integration area of study. Anti-differentiation is back better than ever. So the other things that we need to talk about, you can't just model any old function as a probability density function. You can't just take anything and find the area under it and say that's a probability. There's a couple of things that need to happen. First of all, you'll remember from discrete random variables, what were the properties that this table had to have? You'll remember that all of these probabilities, they had to be between 0 and 1, including 0 and 1, and they all had to add up to 1. So that's pretty much the same thing when we're looking at a continuous random variable and a probability density function. If we're going to model a function as a continuous random variable, as a probability density function, then the whole function needs to sit above the x-axis. So the whole thing needs to be above the x-axis, and the area under the whole thing needs to equal 1. So that's what we're talking about here. So the function needs to be above the x-axis for everything in our domain, okay? And our domain might not be R, we just might be interested in, for example, this one where x is 0 to 24. So it needs to sit above the x-axis, and the area under the whole curve needs to be 1, okay? Actually, we'll look at an example right now. Let's go. So here's an example. We're looking at the time spent in minutes in 1 hour looking at social media for a particular person. Doesn't really matter so much. So our random variable is x. Now you can see I've got a domain here from 0 to 60 because by my definition, you cannot spend more than the amount of time spent in 1 hour, it can't be more than 60. It doesn't make sense. So anywhere between 0 and 60 is where my function is valid. And it's being modeled by this cubic. Now, if I sketch that section of the cubic there, obviously my cubic would keep going. I think it looks like that from memory, but I'm not interested in that. I'm just interested in the cubic from 0 to 60. Now, this is important here as well, because my function, as I'm defining it, if you look at my rule for a continuous random variable, we know that the area under the curve from negative infinity to positive infinity needs to equal 1. So if my function only goes from 0 to 60, all I do to get around that is I just say from 0 to 60, I want to use this cubic, and everywhere else, I just want the function to be at 0, okay? Because then when I'm integrating from negative infinity to positive infinity, I can actually ignore the bits that are all 0. so I don't bother. So what I can do here, if I just want to test, is this function that I've defined, is this a valid probability density function? Well, first of all, is the whole thing above the x-axis? Yes, it is. And secondly, is the area under the curve 1? So I can just integrate. So if I integrate in my calculator from 0 to 60 of that function, I get 1. So yes, it's a valid probability density function. So that's an example where we're going from 0 to 60, where we have a very specific domain. I just want to show you another example. So here's an example where our domain actually goes off to infinity, which doesn't seem like it would work, but it does in this instance and in a lot of instances where you will be looking at. So let's say X is the kilograms of pizza that somebody ate in 1 week. So this could very well be me. I like to eat a lot of pizza. You can see, a lot of weeks, we're not eating too much, and then the more pizza, you can see here it's very, very unlikely that someone would eat, more than 4 kilograms of pizza. Okay, I would hope. So that's what we're modeling. And it's an exponential function e to the negative x, and the domain is x is greater than 0, because technically somebody could eat 5, 6, 7, 8 kilograms of pizza. It's just very, 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 very unlikely to the point where it's basically 0 is what we're modeling here. Okay, so is the area under there 1? Well, yes, it is. You can actually integrate and use infinity as your top terminal. And what the calculator does is it takes a limit and it says that that area is basically 1. It's approaching 1. Okay, we'll look at this again later in the chapter when we look at the normal distribution, because that one goes off to infinity actually on both sides. If we're going to do this by hand, this integral, you can actually do that by hand, and I'm going to show you how to do that shortly in the second worked example. So let's have a look. Okay, so our first worked example, we've got a random variable with a probability density function given by this hybrid function here. You can almost always just ignore this second part because it's just 0. Okay, then we will look at one later where there actually are two different functions as a hybrid function. That's a little preview of what's to come. So what are we being asked to do here? We're being asked to show that A is negative 3/4. So how do I show that A is negative 3/4? Well, if this is a valid probability density function, then the area under it is 1. So what I'm going to do is I'm going to integrate across the domain. So 0 to 2 of AX, x minus 2. Never forgetting our dx's. Now, to make this a little bit easier, I'm going to chuck the a out the front. Sorry, I want to set that equal to 1, don't I? So I'll put that there. And I'm going to expand it as well, because then it's a little bit easier to anti-differentiate. So if I anti-differentiate x squared minus 2x, I get 1 on 3 x cubed minus x squared. 0 to 2 are my terminals. Let's make that 1 on a, so the a is out of the way. Now I'm going to sub in 2, which gives me 1 on 3 times 8 minus 4. And then when I sub in the 0, I just get zeros everywhere. So let's say I get 8 on 3 minus 4, which is 12 on 3 equals 1 on a. So 8 minus 12 is negative 4. So negative 4/3 equals 1 on a. So that would mean that a equals negative 3/4, bang, which is what I was looking for. So there we go. Okay, so for the next one, this is the one I was talking about where we're going to need to use some limits. So what are we going to do here? So show that this is a valid probability density function. Well, the upper terminal is infinity. So what I'm going to do is I'm going to find the integral from 0 to k, and I'm going to look at what happens as k approaches infinity. You might have seen this way back when you first got introduced to differentiation, when you did first principles. You might have looked at limits. Similar idea here. So we're going to look at what happens to this integral. And hopefully we get 1 if we've got it right. So we'll leave that limit where it is. It's not going to do anything till right at the end. I'm going to anti-differentiate 3e to the negative 3x. So the antiderivative of e to the negative 3x is negative 1/3 e to the 3x. So that gives me 3 times negative 1/3 is negative 1. So negative e to the negative 3x 0k. And now because you can't sub infinity into something, so what we do is we just make it k. So negative e to the negative 3k minus negative e to the 0. So negative e to the 0 was negative 1. So I'm going to end up with, I've forgotten to write my limit there. I hope you'll forgive me for that. We've got to have our limit until we don't need it anymore. So what happens here is we get negative e to the negative 3k plus 1. E to the 0 is a 1, and the two minuses will become a plus. So negative e to the negative 3k. So what's going on there? So what happens to this expression as k gets really, really large? Well, as k gets really, 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 really large there, I get e to the power of a really, really large negative number, or negative e to the negative 3k. Now, if you actually sketch negative e to the negative 3k, just to help you out here, so e to the k would look like that. So if it's back to front and upside down, it would look like this, okay? And we can see what happens as k gets really, really large. This here is just basically becomes 0, okay? So as k approaches infinity, negative e to the negative 3k approaches 0. So if you sub in, if you're not sure, you can just sub in a really large number for k and you'll see that it's basically 0. So what we say is that as a limit, this equals 1. That's it, okay? So it's basically 1 as k gets really, really big. So we say that the area under the curve from 0 to infinity is 1, which is what we were after. Okay, a little bit tricky. Hopefully there's not one like that on the exam, because it can be tricky with these limits. But you know how to handle it now, so good luck. And here's a question for you. Okay, so let's get into calculating some probabilities. We already kind of know how to do it. So let's see what happens. So in order to calculate the probability that x is between two values, we find the area under the curve. We've already talked about that. Okay, so for this example here, we were modeling using a cubic from 0 to 60. I think it was something about the time spent on social media. It doesn't matter, in 1 hour, so between 0 and 60 minutes. If I want the probability that x is between 20 and 40, all we do is we find the area under the curve. So we integrate from 20 to 40. And in that case, it was around about 0.481. So we can do that by hand. If it's a friendly function, it's not too bad to integrate, or we'll use our calculator for some trickier examples on the second exam. A couple of things to remember. It does not make sense to say that the probability of x is equal to something. You won't be asked what's the probability that someone spends 41 minutes on social media in 1 hour. You'll be asked what's the probability that they spend between 38 and 42, or more than 41, less than 41, and so on and so on. The other thing to note that because of that, because it doesn't make sense to say that x is equal to a, that would mean that the probability that x is less than a and less than or equal to a are actually the same thing. There's no distinction between the two. So you'll see I had less than or equal to and then less than there. They could have both been less than, they could have both been less than or equal to, all the same thing. They all have the same answer. So even though it might sort of stipulate in the question more than 40, and then you put more than, if you had written more than or equal to 40, you'll get the same answer. But we should write what is actually being asked for in the question, but we just note that there's no distinction there between the two. The other thing that's really useful, as it was with discrete random variables, is that the probability that x is less than a is equal to 1 minus the probability that x is greater than a. That can be quite useful for a function that goes off to infinity. So instead of having to use a limit, so let's say that the domain was 0 to infinity. Instead of, when I was asked the probability that x is, say, greater than 3, instead of using infinity, it'd be easy to do 1 minus the probability that it's less than 3, because then I'm only going 0 to 3. Okay, does that make sense? So we can be a little bit clever with that fact sometimes, and we do really need to use it for some questions. So let's look at a worked example. Okay, so we're going to use this continuous random variable. It's being modeled as a circular function, so exact values are going to come into play here for the 5,000th time this year. I want to know the probability that x is less than pi on 12. So some astute people might recognize that this is actually going to be a symmetrical function from 0 to pi and 6 if you have a look at it. So I would wager that the answer is actually going to be 0.5 because it's just going to be half of that area. But let's confirm that with some integration. So we are looking for 0 to pi on 12 of 3 sine 6x is what we are calculating. Now, the antiderivative of sine of 6x is negative 1 on 6 cos x. So I get negative 1 on 2 cos 6x from 0 to pi on 12. I like to be really careful when I'm doing my substitutions. Oops, that should be a 12. So 6 times pi on 12 is pi on 2. And then I'm using lots of brackets here to make sure I don't miss anything. It's really tempting because that's 0 to assume that the second bracket's just all going to be 0. It won't be though, because cos of 0, of course, is 1. So be careful there. Don't just assume that if the second terminal is 0, that the whole second bracket will disappear. And in fact, it's the first one that's going to disappear because cos of pi on 2 is 0. So I get negative 1/2 times 0 minus negative 1/2 times cos of 0. So minus negative 1/2, which is 1/2, which is what we were expecting based on the graph. So there we go. 1/2 is an answer. Let's have a look at another one with some conditional probability. Okay, so we're going to look at conditional probability now. We treat it exactly the same way as we have in the past, in that the probability is equal to the probability that both things happen divided by the condition happening where x is less than pi on 12. Now, the denominator we already did in the previous question, so we really just need to work out the probability that x is less than pi on 24 and then divide it by 0.5, which was, again, the previous question. So how do we get less than pi on 24? We're going to need to anti-differentiate again. Now, I already anti-diffed it in the previous question, so I can save some time by just copying my working from before, which was negative 1/2 cos of 6x for pi on 24 to 0. So what do we get here? We get negative 1/2 cos of pi on 4 minus negative 1/2 cos of 0. Running out of room here. Okay, so cos of pi on 4 is 1 on root 2, so that first bracket will become negative 1 on 2 root 2 minus negative 1/2. Of course, cos of 0 is 1, as we said before, so that gives me plus 1/2. So running out of room, we move up here. So my numerator is negative 1 on 2 root 2 plus 1/2, which we are dividing by 0.5, which is the same thing as timesing by 2. So the probability is negative 1 on root 2 plus 1. Okay, bit of a weird answer. Of course, if it was a calculator task, I would just have an answer as a decimal, probably round to 3 or 4 decimal places. But this is a non-calculator question, and that could be on the first exam, and the answer would be negative 1 on root 2 plus 1. Okay, so there we go. That's the probability. Okay, so to sum up the lesson, a random variable is continuous if it can take any real value over an interval. What we mean by that is that if I keep measuring it closer and closer, it could actually go to an infinite number of decimal places. So it doesn't really make sense to say that the probability of x is equal to one thing, because technically it could be an infinite number of things across my domain, whatever that domain may be. Okay, so an easier way to think of it, again, is things that we would measure. So height, weight, time are continuous random variables. If you're doing general maths, this would come up in the statistics unit of that subject as well, funnily enough. Now, a probability density function is where the function that we have to model our probability distribution, the whole thing has to be above the x-axis and the area under the whole curve needs to equal 1. And of course, to find our probability that x is between two values or greater than or less than, we use the area under the curve. So the probability that it's between A and B would be the area under the curve, the integral from A to B of f of x. back to our joke from the start if you didn't get it. So all of our functions are having a great time. They're partying, they're getting to know each other. But poor e to the x is over here in the corner, a little bit sad. X squared goes over to e to the x and says, dude, what's going on? Why are you so sad? Why don't you integrate? And e to the x says, what difference would that make? Of course, it's funny because the integral of e to the x is e to the x. So what difference would it make? It wouldn't make a difference if e to the x integrated. It'd still just be e to the x. And I know what you're thinking. What about the plus c? Forget about the plus c. Don't ruin my joke, okay? I'll see you next time. Hi Methods friends, how you going? So if you studied Methods last year and you used Edrolo, you would have met my daughter Charlie, and I talked about how in the first couple months of her life, her height was growing exponentially and I was getting a little bit worried. But here she is now. She's very tall, but she's very, very cute and she's walking around and everything's going very well. We went to the nurse the other day and they said that Charlie's height is in the 99th percentile. So what does that mean? And what are the chances that she's going to be the tallest kid in school? We'll find out at the end. Okay, so this lesson's called the center and spread of continuous random variables. We've looked at center and spread in two contexts before with our discrete random variables and then our binomial distribution as well, which is another type of discrete random variable. And so let's apply it to continuous random variables. Let's go. Okay, so we're going to be looking at calculating the mean, calculating the variance and the standard deviation. We're also going to look at this idea of a percentile and some other types of problems that we may come across. So what are you waiting for? So first of all, we're going to be looking at the mean. Now, we talked about the mean in the context of a discrete random variable, this idea of the expected value. So the expected value of our continuous random variable is the long run average. It's what we're expecting to happen each time we run our experiment. If we're flipping the coin and looking at how long it takes to hit the ground, how long are we expecting each time? So if we generated heaps and heaps and heaps of values of x, if we flipped 700,000 coins and we wrote down how long it took to hit the ground every time, we added all those up and divided by 7,000, that would be pretty close to the mean. We could calculate it using our formula. So we often use our calculator to find the mean because it's a little bit easier. And if you look at the formula here, what we have to do is we find the area under the curve, but we multiply our function by x. Now, you'll remember that the mean of a discrete random variable was x times the probability of x, and we took each value and multiplied it along the table. Now, it's kind of the same thing here. We're doing x times the function and finding the area under the curve. So it's kind of easy to remember. But the reason we use our calculator is often just taking our function and multiplying it by x makes it a lot harder to anti-differentiate. But there are cases where that does not happen. So we will look at some examples where we do it by hand as well. We also looked at this property back in the previous chapter about the linear combination of random variables. I'm just putting that there to show you that that property does also work for continuous random variables, although we won't really be looking at it in any more detail than that. So let's have a look at an example. So here's our example. It's the same function from the previous lesson, the time spent in minutes in 1 hour looking at social media. So our function could be anything between 0 to 60. We had a look at what it looks like. Now, if we want to find the mean using the formula, we need to integrate from 0 to 60 of x multiplied by f of x. So I need to take this whole function here and multiply it by x. So our cubic would become a quartic. But rather than do that by hand, we're going to plug that into the calculator. So here's my integral. We've got x multiplied by the function from 0 to 60. So I get the mean is 24.857, which is around about here on our distribution. You can see it's not the peak as you might think, but our value is actually here. Okay, so because we've got a lot of probability here, it's shifting us slightly to the right of that peak. So that means that on average, we're spending 24.86 minutes in 1 hour looking at social media. Again, the probability that someone spends exactly 24.857, it doesn't make sense. That is 0. But on average, the expected value, we're spending roughly 24.857 minutes per hour, or this person is whatever we were modeling. Okay, so that's the mean. Okay, so let's look at a worked example. Let's do one by hand that's not too challenging. Now, what you might notice again, in the previous lesson, we looked at a sine function and we found that it was symmetrical. and then we realized that the probability of less than the halfway point was going to be 0.5. So similar thing here. This is also symmetrical, this upside down quadratic. So I would expect the mean is actually going to be 1, okay, which is going to be in the middle, which happens with these perfectly symmetrical functions. Bit of a foreshadowing to the normal distribution later. But let's make sure we get 1. So the expected value of x, the mean, is going to be equal to 0 to 2 of x multiplied by negative 3 on 4x bracket x minus 2. So let's work that out. We'll need to expand it first or make it a little bit easier. So what's that going to give me? That's going to give me negative 3 on 4x squared minus plus 3 on 2 x, and then we've got to expand again. I should have just done this in one line, but that's okay. Sometimes we take longer than we should. Plus 3 on 2 x squared dx. Now we will anti-differentiate, which gives me negative 3 on 16 x to the 4 plus 3 on 3 x cubed. So that'll just be 1 on 2 x cubed. 0 and 2. So let's see, now I need to sub in 2. So the good thing is 2 to the 4 is 16, so that'll cancel with the negative 1 on, so I'll just get negative 3, the 16s will cancel, minus 1 on 2 times 8, which is minus 4, and then the second bracket, everything will just be 0, minus 3, minus 4. I think that was meant to be something else because I'm meant to get 1 as my answer. What have I done wrong? I know what I've done wrong. That should have been plus. Okay, the antiderivative should have been plus, of course. So there we go, negative 3 plus 4 is 1. You know, we're having fun. We're making mistakes. We're fixing them up. We're getting the right answer. So all is good. Time for you to have a go. Okay, let's talk variance and standard deviation. So just as they were previously, I know I'm saying that a lot, we're talking about measures of spread here, and the larger the spread of our distribution, the more likely it is that we'll observe values of x that are further from the mean. Okay, now the formal notation for the variance is this. It's a very gross looking formula there. I'm not going to get you to use it because we're going to use this one. It's much easier, and you'll recognize that as the same formula for a discrete random variable. So it's e of x squared minus the mean squared. The mean you already know how to find, so we will square that and we will subtract that from e of x squared. What is e of x squared? It's exactly the same as the mean, but instead of multiplying by x at the start, I'll multiply by x squared at the start. So pretty straightforward. So we've got x squared times f of x minus x times f of x. Okay, I don't have that notation perfect, but we're multiplying by x squared and we're multiplying by, I forgot the squared sign, and we're multiplying by that mean squared. Okay, so let's have a go. And of course, the standard deviation, which we've talked about before, is the square root of the variance. So time to do a worked example. Again, much more likely that this will be on the second exam or that you use a calculator, because often if you thought multiplying your function by x makes it tricky, multiplying it by x squared will often make it even more disgusting. So sometimes you'll be given part of it and be asked to solve the rest. But, you know, let's get into it. Let's have a go. So this is what I mean by sometimes you'll be given part of it. So for example, I've been given e of x, so I don't need to find e of x squared and e of x and do all of that work. So I've been asked to find the variance and standard deviation. We're going to do this one by hand. So let's find e of x squared first. So e of x squared is going to be 0 to 1 of x squared times negative 2x plus 2. So that's what we are integrating. So we get negative 2x cubed plus 2x squared. So the antiderivative of that will be negative 1/2 x to the 4 plus 2 on 3 x cubed 1 and 0. I've chosen a nice easy domain here because that just gives me negative 1/2 plus 2/3, which is let's see, negative 3, 6 plus 4, 6 is 1/6. So e of x squared is 1/6. So the variance of x will be equal to e of x squared minus e of x squared, which we mentioned already. So that gives me 1 on 6 minus 1 on 3 squared, which is 1 on 9. 1 on 6 minus 1 on 9 is, what is that? 3 on 18 minus 2 on 18 is 1 on 18. So the variance is 1 on 18. And to find the standard deviation, we will square root 1 on 18, which is, let's say, 1 on, let's say, root 18 will be root 9 times 2, so 3 root 2. 1 on 3 root 2. There we go. Rationalize the denominator if you want. I'm not going to. 1 on 3 root 2 looks pretty good to me. 1 on 18 for the variance. And let's have a go for you. Your turn. Okay, so let's talk about percentiles and other types of problems. So in statistics, percentile is the value of x. I'm going to read this. It's the value of x whereby the probability of obtaining a value below this value is a given percentage. That's a real mouthful, isn't it? Essentially what it means is that a percentile is what's below that. So let's say you're the 90th percentile, that would mean that the probability of anything less than that value is 0.9. That's the 90th percentile. Now, a really good example of this is actually your ATAR. When you get an ATAR at the end of the year, that is like a percentile. So example, if you get an ATAR of 85, that means that 85% of people got an ATAR of less than you. Okay, so in other words, you're in the top 15% if you get an ATAR of 85. Okay, so 99.95, you're in the top 0.05% of students. So that's why it's actually impossible to get an ATAR of 100 because you can't be better than yourself. Okay, so that's what a percentile is. So often we'll be asked to find a percentile, but it may not be asked in that way. It may be asked, you may be asked the probability that x is less than something is equal to whatever, and then you need to find the something. Okay, so that could be thought of as a percentile question. Now, the 50th percentile, another word for that is the median. Now, the median is not in the study design, but there's no reason why they couldn't ask you for it in a roundabout way. They could ask you the probability of x being less than what is 0.5, and you'd still need to do it, and you're finding the median without really being asked to find it. So just because it's not in the study design doesn't mean it's not relevant. These problems are usually done with the calculator, but not always. There are times when you can do this. Just like in integration, you would have solved for one of the terminals. You can do that in probability as well. So just really quickly, so what we might be asked to do, let's say we've got our probability density function. I'll just leave it as f of x, and I might be asked to find, well, the probability that x is less than what is equal to 0.9. Let's leave it as 0.9, so that might be the 90th percentile. And what I would do is I would integrate from my bottom terminal, let's just say it's 0, from 0 to a f of x, and I'd set that equal to 0.9, and then I'd need to solve for a. So you've probably done that in the integration unit, and this is another application of it here. So I'm actually going to throw straight to a question for you now, because you've already done this in the integration area of study, and I believe in you. So question for you, here we go. Okay, so to bring it home in this lesson, we were talking about mean, variance, and standard deviation, as we have a number of times in the past. So in the context of our continuous random variable, we use this formula for the mean. So we just basically find the area under the whole curve and we chuck an x out the front of the function. We multiply the whole function by x. If we want to find the variance, it's the exact same formula as for discrete random variables, just in our integration context. So we chuck an x squared out the front of the function and integrate, and then we subtract the mean squared, as we have done before, and you've seen in a couple of examples. Okay, we've talked about what a percentile is as well. And we have looked at how we might calculate values of a, for example, such that this is, whatever we want. Okay, and what we do is we set up an integral where we're solving for one of the terminals. Okay, so hopefully that all made sense to you. Okay, my daughter Charlie, here she is. We know she's in the 99th percentile for her height. So what does that mean? That means that the probability of someone being taller than her is 0.01. Okay, so if we think about what are the chances that she's going to be the tallest girl in her class, well, let's just say there's 20 kids in the class. So that would be, there's a 0.99 chance that a student is shorter than her. So 0.99 times 0.99, if we do that 19 times, it's 0.83. So by my calculations, there's an 83% chance that my gorgeous girl is going to be the tallest girl in her class. Maybe what's more interesting, what's the probability that she'll make it to the WNBA? That's a question for another time. I will see you shortly for the normal distribution. Okay, catch you soon. Hi Methods friends, how you going? Have you ever seen an argument similar to this in the yard around your school? The general maths students talking about how he got 89% on his latest SAC. The methods students talking about how he got 82%, but that's actually better because methods is a harder subject. It's an argument as old as time, or as old as the VCE. So how can we solve this? How can we decide who actually did better? We're going to use something called the normal distribution, and we're going to settle the debate once and for all. Okay, so this lesson is called the normal distribution. It's the last type of distribution we're going to look at in this course. There's nothing normal about it. It's very, very special, and it's the most famous distribution there is. So let's get into the lesson. Okay, so we're going to do 3 lessons on the normal distribution. The first one, we're going to be talking about what it is, understanding how it works, what does it look like. Then we're going to look at what happens if we play around with some of our variables, the mean and the standard deviation. Then we're going to look at something called Z-scores and standardization. So I hope you stick around till the end because it's going to be a good time. I tell you, normal distribution, I love it. Okay, so understanding the normal distribution, what are we talking about when we talk about if something is normal or normally distributed? You might have heard the word bell curve before. So the bell curve, it looks like this. It looks like a bell. So if something is normally distributed, it means that we can assign this kind of symmetrical distribution to it. Okay, it's the most commonly used and it's the most useful type of continuous probability distribution. And what happens in the real world is a lot of things approximate a normal distribution if you look at them closely enough. So if we look at a big enough sample size, a lot of the time, our distribution will become more and more symmetrical and it'll end up approximating this bell curve. So here's a really quick example here. If you flip a coin 10 times and you look at the probability of it being once, twice, 3, 4, 5 numbers of heads, if we do that more and more and more and more times, 100 times, 1,000 times, the distribution gets more and more symmetrical. You can already see it looks approximately normal here. And what happens if we flip a coin enough times, we actually can use a normal distribution to work out the probabilities rather than a binomial distribution. But that's getting into the next chapter, which I'm not actually running through with you, so I don't want to step on that presenter's feet. I'm sure they're going to really bring it home for you. So let's talk about the normal distribution. It's characterized by its mean and its standard deviation. So every normal distribution looks exactly the same. It has this curve. All we do is we fiddle with the mean and the standard deviation. The mean will shift it to the left or the right because that will change the center, and the spread or the standard deviation will make how flat it is, okay, or how shallow it is. So the standard normal distribution is what we use. Everything is measured from the standard one. So we've got this basic bell curve, our standard normal distribution, which has a mean of 0 and a standard deviation of 1. So we say that every normally distributed variable is some sort of transformation of that standard one. And we use Z for the standard one. And we're going to talk about that later when we talk about Z scores. Okay, so you often see Z used for the standard normal distribution. So it's just a bell curve with a mean of 0, standard deviation of 1. So you can see it's symmetrical about the y-axis there. Okay. The other thing that's useful to talk about here is that function. So just like our continuous random variables where we had functions, we were looking at cubics, we were looking at circular functions. Our normal distribution, this is the formula for a normal distribution. Now, the good news is you don't need to memorize that. And the even better news is you don't need to anti-differentiate that. You don't even need to plug it into your calculator and find the integral. You use something else in your calculator, which we will get to. It is useful to know this function, and we're going to look at transformations of the function just so we can see where the mean and the standard deviation kind of come from. But you do not need to memorize that, so don't stress if you look at that function and you get the sweats. Okay, so I'm going to give you a question now, so let's get into it. So let's look at transformed normal distributions now. So this is basically all of our normally distributed variables. So if we take any normally distributed variable and we know what the mean is and the standard deviation is, we can plot it as a normal curve. So if we have a look at this picture here, the pink distribution, that is a normally distributed variable with a mean of 10 and a standard deviation of 2. And the green one has a mean of 6 and a standard deviation of 3. So you can see the 6 and the 10, you can see where the means are. It's the middle of the distribution. And because the green one had a larger standard deviation, it is more spread out. Now, this notation here is really important. You'll recall from the binomial distribution, we said that things were binomially distributed with number of trials and a probability of success. The other notation is for a normally distributed variable, which has a mean and a variance, which we write as the standard deviation squared. Okay, so that is the notation. So if you know the standard deviation, I will actually literally write 3 squared. I won't write 9 because then that's putting it in this in that same form there. Okay, I'm not sure that it matters too much, but that's a really nice way to demonstrate that you know the notation properly. Okay, so how do we get to these transformed distributions? Well, if we're going to move something, the mean, then we're moving the function to the left or to the right. So that'll be a translation of mu, the mean, in the positive direction of the x-axis. Could be the negative direction, of course, if the mean was negative. And the way that we get our standard deviation is by dilation from the y-axis and from the x-axis, which flattens it out. Now, do you really need to know that? Not overly, but now you can see, here's my transformed normal distribution, and you can see there's my horizontal translation, and here are my dilations. So if you're given a function, and I'm about to give you one, that's normally distributed, you can just read off the mean and the standard deviation from the function. But generally that won't come up all that often, but it is going to come up here because I've just shown it to you. Okay, so lastly, this important fact down here, we're going to come back to it when we talk about z-scores. But you can see here, if we take our value of x and we subtract the mean and the standard deviation, that would mean that the probability that our normally distributed variable is less than a, that would be the same thing as our standard normal random variable being less than a minus the mean divided by the standard deviation. Don't worry too much about that yet. It's going to come up later in the lesson, but it is relevant to what we're talking about here, okay? But it'll be much more important when we look at z-scores, okay? So here's a question for you. I'm going to get you to have a look at one of these and tell me the mean and the standard deviation, okay? Let's have a go. Okay, so standardization and z-scores. So really, really important idea in this part of the chapter is this idea of standardized values. So a standardized value is a statistical measurement that describes the value's relationship to the mean. What does that mean? Basically, what we do is we look at our value, and a standardized value is saying, well, how far is that from the mean? Okay. So let's say I've got a normally distributed variable with a mean of 10 and a standard deviation of 4, and I want to think about the value of, 18. So 18, how far is that from the mean? Well, it's 8 away from the mean, but the number 8 doesn't really mean anything. What's more valuable to say is it's not 8 from the mean, it's 2 standard deviations from the mean. Okay, that's much more valuable in statistics as a measurement. So because the standard deviation is 4, 2 lots of 4 is 8. So we are the mean plus 2 standard deviations. So that's what a standardized score is. We would say that this as a standardized score is 2 because it's 2 standard deviations above the mean. If I had the value of 2 would be 2 standard deviations below the mean. So as a z-score, that would be -2. I've got too many 2's there. I know that's a bit confusing, but let's look at this formula here. So the standardized value is how many standard deviations from the mean am I? So the way I work that out is I work out, well, what's the difference between my value and the mean? So my 18 minus 10 would be 8. So I'm 8 from the mean. Divide that by how many standard deviations. So if the standard deviation is 4, I'm 2 standard deviations from the mean. So that's the formula, okay? So it's really, really useful because it can help us kind of compare things in a fairer way. So for example, your study scores, you're studying lots of different subjects that are all different and thought of as different difficulties. So if we can get a way to put you on the same scale, which is a study score out of 50, and then we can kind of compare those scores a little bit fairer. So for a study score, 30 is the median study score. So that would mean that if you get a 30, then the 50% of the people are below you, 50% of the people are above you. So you could think of that in this context as a standardized value. If you get a 30 on a subject, then your Z score is 0, okay? It's not really quite how they calculate it, but that's just kind of a comparison for you. So a Z score is how far from the mean are you in terms of the number of standard deviations. It really just comes down to that, okay? So let's look at a worked example. Okay, so the worked example we're going to be looking at is about a machine that is putting caffeine into an energy drink. So the amount of caffeine in milligrams that the machine puts in each can is normally distributed, and that we're calling that C. Our random variable is C. So C is normally distributed, and what we've done is we've set the machine, we've told it to have a mean of 65 and a standard deviation of 3. So C is normally distributed with a mean of 65 and a standard deviation of 3. So I can write it like that. C is normally distributed. So what I've been asked to do, determine the Z score for a randomly selected can with a caffeine content of 60.5. So we've grabbed a can, we've tested it. It's got 60.5 milligrams in it. How far from the mean is that? Is that really extreme? Is that not really that extreme? If the standard deviation was really high, then it wouldn't be that unusual to get a can content of 60.5. If it's a really small standard deviation, then that might be quite unusual to get a can. Okay, does that sort of making sense? So, but let's look at the Z score. So remember the Z score formula, X minus the mean divided by the standard deviation. 60.5 is what we observed. That's my X minus the mean divided by the standard deviation, which is 3. So the difference between 60.5 and 65 is 4.5. So that'd be negative 4.5 over 3. So that would be negative 1.5 is my Z score. So this particular observation, 60.5, that was 1.5 standard deviations below the mean. So here's my normally distributed random variable, that's 65. So 60.5 is here. So that would be the same thing as on my standard normal distribution. There's 0, that's negative 1.5. It's the same distance from the mean. Okay, so that has implications that I'm just kind of getting at subtly, that area there would be the same thing as that area there. So the probability of a can having less than 60.5 milligrams would be the same as the probability that Z is less than negative 1.5. We'll look at the implications of that soon. So another example. Okay, so here we're going to use kind of what I was just hinting at. So same situation, same coffee machine, but now I've been told that the probability that Z is less than 2 is approximately 0.977. So that's actually a true probability that's been worked out. So if I was to draw a picture, here's 2. So here's my standard normal variable. There's the Z score of 2. So that area is roughly 0.977. I've been told that in the question because this is a non-calculated question. I couldn't work that out. So using that information, calculate the probability that a can will contain more than 71. So 71, first of all, what is that as a Z score? 71 minus 65 divided by 3. 71 minus 65 is 6. So that is 2 standard deviations. Not a coincidence, that's 2, and I've been told that. So what I want is the probability that X, sorry, not X, get too used to using X. You got to be careful if you're using X all the time because you're used to it in lots and lots of questions where you use X as the default, that you don't accidentally use it when it is really C or something else, okay? So the probability that C is less than, sorry, I want more than, don't I? Oh, making all sorts of mistakes. All right. C is more than 71 is what I'm trying to work out. Now, that's the same thing as the probability that Z is greater than 2, okay, is what we're using with this Z score. The probability that a can being greater than 71 milligrams is the same thing as the probability of a Z score being greater than 2. Now, I happen to know the probability that a Z score is less than 2, which is 0.977. So that would mean that 1 minus that is actually what we're looking for. So the answer to our question is 0.033. And by 3, I mean 023. Okay, there we go. Question for you now. Okay, so to sum up the lesson, the normal distribution is the most commonly used, it's the most useful, it's the best, it's the most wonderful type of continuous probability distribution. Okay, we see it all the time in the real world, and it's how we're going to be finishing off our work on continuous random variables. Okay, I was going to say it's how we're finishing the course, but we're not. There's still a chapter to go. I keep forgetting that. So this is the notation we use for normally distributed variables, where we have the mean and the standard deviation squared listed there. Same thing as the variance. Z scores, really, really useful thing to be using, and they're going to come up again in the next couple of chapters. So our standardized value, or Z score, tells us how many standard deviations from the mean a particular value is. Okay, so we're measuring in standard deviations of distance. Okay, rather than how far from the mean are you? Who cares how far from the mean are you? It really depends on the spread of the distribution as to tell whether that's a lot or not. Okay, so we talk about things in terms of how many standard deviations away we are. Okay, so that brings us back to our two people in the yard here. They are arguing about who did better on their test. Of course, we can settle it by converting their scores to Z scores, standardize their scores, find out from the teacher what was the mean and what was the standard deviation. We are, of course, making some assumptions here that their distributions are normal and that we can compare them fairly and whatever, but we just want the two students to stop arguing. And this is how we can do it. Compare it with a Z score. And then, of course, they can compare their study scores at the end of the year. Who was the ultimate maths king? I think it's going to be you. And I'll see you next lesson. Okay, bye. Hi, Methods friends. How you going? So I've been teaching VCE for over 15 years now. I know I look young. And every year, without fail, a student in my class will raise their hand and ask, Mr. Wilson, what's with your eyebrow? Usually a kid like this. Look at the little smirk on his face. Anyway, one of my eyebrows is white. It's a pigment thing. Okay, let's move on. So I started crunching the numbers, and I reckon this is a normal random variable. It happens every year. It usually happens after around 20 lessons, give or take 5. So if you've been watching me since Unit 1, what's the probability that you hadn't noticed yet? Here's the random variable, and we're going to answer the question at the end. Okay, this lesson's called Using the Normal Distribution. We're going to do exactly that. We're going to use the normal distribution. So let's get stuck in. So we're going to be looking at two things in this lesson. We're going to be looking at calculating probabilities with the normal distribution, and we're going to be looking at using symmetry. When we're looking at calculating probabilities, we're looking at more of using the calculator, and using symmetry, we'll be looking at calculating probabilities, but more so for the non-calc exam. Okay, so what are we waiting for? So calculating probabilities with the normal distribution, how do we do it and how is it different to other continuous random variables? Well, you'll remember from continuous random variables, to calculate the probability that x is between two values, we calculate the area under the curve. Now, there's no difference here. The normal distribution, we still calculate the area under the curve. The difference is the way that we do it. We don't actually use the function, the e to the, I can't even remember what it is, that big messy looking probability density function from the previous lesson. We just use a function in the calculator because the normal distribution, the only difference is your mean and your standard deviation. We've got a function in the calculator that will work it out for you. You just plug in the mean, you plug in the standard deviation, and you plug in your values, and it spits out the probability for you. It's very nice and straightforward. Now, you can calculate to Z scores and use the standard normal distribution, and I'll show you what I mean by that. So let's say we have a discrete random variable that has a mean of 10 and a standard deviation of 2. Now, so we'd write that. If I wanted to work out the probability that x is greater than 14, this is what the calculator will do. I put in that I want to calculate the probability that x is between 14 and infinity with a standard deviation of 2 and a mean of 10, and it spits out the answer for me, which is 0.2275. Now, 14 in this case would have a z-score of 2, so x is greater than 14 would be the same thing as z is greater than 2. So if I worked out the probability under a normal curve of 2 to infinity with a mean of 0 and a standard deviation of 1, i.e. the standard normal distribution, I will get the same answer. Okay, so just to show you that you could convert it to a z-score and always use a mean of 0 and a standard deviation of 1, but the calculator will let you put in whatever mean and standard deviation you want. Okay, so let's have a look at a worked example, and hopefully this will sink in for you. Okay, so we're talking about the amount of caffeine in milligrams that a machine puts into each can of a company's new energy drink. You'll remember we used this example in the previous lesson, but now we're going to calculate some probabilities. So again, the machine's set with a mean of 65 and a standard deviation of 3. So we can say if we our random variable C, we can say is normally distributed with a mean of 65, standard deviation of 3. Okay, so what we are being asked to do is determine the probability that a randomly selected can will have a caffeine content of less than 60 milligrams. So we're looking for the probability that C is less than 60. Okay, so we could work out what that is as a z-score. I don't really need to. Okay, I'm just going to plug that into my calculator and I'm going to have the answer. Okay, so let's do that now. All right, so we're going to be in the interactive menu. If we are in the using the class pad, it'll look slightly different if you're using a different device. So what we want is less than 60. So our lower, you would think that we would use 0 here, but we're actually going to use negative infinity because the domain of the normal distribution is negative infinity to positive infinity. Even though I can't have a caffeine content of less than 0, I still put negative infinity here. If you put 0, it probably won't change your answer to 4 decimal places, but we should always use negative infinity here just in case it affects our answer. So the upper will be 60. And then we put in our mean and our standard deviation, so 3 and 65, and then there's our answer there. So we get 0.0478 to 4 decimal places. So that's what I would write on my paper if this was a second exam. Not a lot of working needs to be shown here. Okay, so there we go. Let's look at another one. Okay, so for part B now, we're going to determine the probability correct to 3 decimal places that our randomly selected can will have a caffeine content of greater than 55, given that it contains less than 60. So we've got a conditional probability question. So I'm not going to do my C is distributed normally again, because I already did that in part A. That doesn't need to be part of my working. I'm going to say that what I'm trying to work out is the probability that C is greater than 55, given that C is less than 60, which is a probability that both things happen divided by the probability that the condition happens, which we've been doing for ages. So if it's going to be greater than 55 and less than 60, it needs to be between 55 and 60. And we are dividing by the probability that C is less than 60. Now, C is less than 60. That is our answer to the previous question. What I want you to be careful of is don't use your rounded answer here. So don't use 0.0478, use the unrounded version. So in the calculator, what I will do is I'll do another calculation. This time my lower will be 55, my upper will be 60, and I will still have 3 and 65. And then what I will do is I will divide one by the other. So I want to do this answer here, and I want to divide by my answer to part A. So I've gone to heaps and heaps of decimal places. So I know I'm super, super accurate. And now I'll round this to 3, which is 0.991. And that is our answer. Okay, so there we go. Time for you to have a go. Okay, let's move on to some non-calculator questions. So we're going to be looking at the symmetry of the normal distribution, which is really, really useful to answer lots of problems if we know the right information. So a couple of things to remember that we've talked about before. The probability that x is less than A is 1 minus the probability that x is greater than A. And we know that probability x is less than the mean is 0.5. We just talked about that in the multi-choice question. So some other really useful things to think about have a look at this diagram here. We can see that this blue area here is the same as this blue area there. So where -1 is 1 standard deviation below the mean, and 1 would be 1 standard deviation above the mean. So the probability that Z is greater than 1 is the same thing as the probability that Z is less than -1. And we can extend that to any value of Z, which is what we're talking about here. The probability that Z is less than -A is equal to the probability that Z is greater than A. So really useful. And even more useful, we can extend that to think about any normal distribution, because instead of, let's say, instead of the standard normal distribution, let's say we were looking at a normal distribution with a mean of 10. So if I went 3 above the mean to 13, and 3 below the mean, doesn't even matter what standard deviations I'm talking about, what the Z scores are, that area there should be the same as that area there. They are the same distance from the mean. So the probability that X is less than 7 would be equal to the probability that X is greater than 13. So that's what we're getting at here, that the mean minus some number versus the mean plus that same number, the same distance from the mean, those tails, the probabilities will be the same. Okay, the other thing we can look at is in this pink box here. So this area here you can hopefully see is the same as this area here. So going 1 standard deviation below the mean and 2 up is the same area as going 2 below and 1 up. We've just shifted that probability. You can see it's a mirror, if you like, if you flipped it over. They're the same area, and you can use that kind of tip to your advantage as well. So back to my 10 and my 7 and 13, let's say I went down to, I don't know, stick with the 7, and then up to 15, between 7 and 15, so 3 below the mean and 5 above the mean would be the same as from 5 to 13. I hope that makes sense. So if I went 5 below the mean and 3 above, so those two areas would be the same. So you see what I'm getting at here? If we've got two, we can use these facts that those two areas are the same. We can also work out sometimes what the area in between is, or on the outsides. It's really, really useful with questions that we'll look at in a minute to just draw a diagram, draw up a normal distribution. You can even get marks for your diagram sometimes if it's worth a couple of marks, and shade in what you know, and you can usually work out the areas that are required. So let's have a look, and hopefully it makes a lot of sense, okay? Okay, let's have a look at a worked example. So X is going to be a normally distributed random variable with a mean of 72, standard deviation of 8, and Z is the standard normal random variable, as we usually call it Z. And I want to use this result here, that the probability that Z is less than 1 is equal to 0.84. That is something that I have been told. I could confirm that with my calculator, but this is a non-calculator task. So I've just been told that for a standard normal distribution, which has a mean of 0, the probability that Z is less than 1 is equal to 0.84, okay? Now my question, what's the probability that X is greater than 80? So 80, what is 80 as a Z score? So 80 minus 72, so which is the mean, divided by the standard deviation is 1. You shouldn't need the formula to work out that 80 is 1 standard deviation above the mean. The standard deviation is 8. So clearly 72 plus 8 is 80, okay? But what do I know? That means that the probability that X is greater than 80 is the same thing as the probability that Z is greater than 1. So what is the probability that Z is greater than 1? Well, I've just been told that the probability that Z is less than 1 is 0.84. So I'm looking for this area in here, which is 0.16. So that's going to be the answer to the question. So what is my working like? I'll continue on from here. I'd say Z is less than 1. Which is equal to, Z is greater than 1, which is equal to the probability that Z is less than 1, which is equal to 1 minus 0.84 equals 0.16. Probably more working than I needed there, but you can see exactly where my 0.16s come from. So that's how we do it. We convert our number to a Z score, and then we use the probability that we've been given and do something with it, okay? We might be doing 1 minus it, or we might be, who knows, okay? Let's look at another one and keep going. Okay, so this one will be a little bit more challenging, but hopefully not too bad. So exactly the same situation, and I've still got the same information. I know that Z is less than 1 is equal to 0.84. So that's 0.84, where that's 1. And we also know that if we change that to our actual normal distribution, which is 72, then 1 above would be 80. Now, what are we being asked for here? We're being asked for the probability that X is between 64 and 72. So where's 64? 64 would be here. Now, 64 is 1 standard deviation below the mean. So the probability that X is between 64 and 72 is the same thing as Z is between -1 and 0. Okay, so how am I going to work that out? Well, I know that if I want to go between here and here is what I'm trying to work out. Now, I know that less than 80 is 0.84. I did that in the previous question. So it would also give me, I knew that in there, I just don't want to put too much on my diagram here and confuse you. So I know that that's 0.16. That's actually what we did in the previous question. So if you look on the other side, then that would have to be 0.16 in here. The probability that X is less than 64 would have to be 0.16. Okay, so how does that help me? Well, I know that the mean is 72, so the probability that X is less than 72 is 0.5, and less than 64 is 0.16. So my answer, which is between 64 and 72, would have to be 0.5 minus that 0.16. That's what my answer is going to come from. So we can do it this way if we like. We can say that the probability that X is between 64 and 72 is the probability that X is less than 72 minus the probability that X is less than 64. And those things I already know. So 0.5 less than the mean. And from my diagram, X is less than 64 is 0.16. So 0.5 minus 0.16 is 0.34. So there's my answer. Okay, there'd be different ways to go about this, and you might have done it differently. You might have used different values or different regions. Doesn't matter, so long as it makes sense what you've done, and a diagram can be really useful here, as I said, and it's really logical the way your argument flows and you arrive at the same answer. Hopefully you would be all good to get full marks. Okay, I think I got one more for you. So part C, we're now looking at conditional probability. So the probability that X is less than 64, given that X is less than 72. So less than, we're going to use what we've already worked out. So less than 64, given that it's less than 72, would be less than 64 divided by less than 72. Now, without doing all the working again, we had 64 as down here with 1 standard deviation below the mean, and less than 64 was 0.16. We've done that in a previous question. And less than 72 would be 0.5. So what I get here is 0.16 divided by 0.5. Dividing something by half is the same thing as doubling it. So I get 0.32. Okay, there we go. Time for you to have a go. All right, so to sum up the lesson, when we're calculating probabilities using the normal distribution, we're still finding the area under the curve, but we're not actually integrating. We're using the function on our calculator. So depending on which calculator you use, make sure you're quite familiar with that. A note with the class pad that when we do our lower and our upper bounds for the probability, if it's greater than something, we use infinity as our upper bound. And if it's less than something, we use negative infinity as our lower bound, making sure we have the correct standard deviation and mean. Really easy to accidentally use the variance, so make sure you have a look at what you've been given. With our non-calc questions, we are using the symmetry of the normal distribution. We might be using one of these two properties or another one that we come up with. So, for example, the probability that Z is less than -1 is the same thing as Z is greater than +1. So if we've got the same distance from the mean on either side, those two probabilities of the tails will be the same. And of course, 1 minus those two tails would give you the middle. Okay, so whatever it is that you're looking for. Of course, we can do some similar things here. If we've got one above the mean and two below, or one below and two above, we can say that those two probabilities are the same as well. Okay. All right. Going back to my eyebrow, you'll remember I said that that it's normally distributed, how long it takes for somebody to say something to me in class, with a mean of 20 and a standard deviation of 5. Now, this is my 31st video for Edrolo. So if we worked out the probability that we hadn't noticed for more than 31 lessons, then that probability is 0.01. So very unlikely that you hadn't noticed. And I thank you for just concentrating on the maths and not looking at my eyebrow. Really appreciate it. Good news, I've only got one lesson left. So let's make it a great one. It's been a pleasure getting to know you all virtually. And I'll see you back here soon. Hi Methods friends, how you going? This is my last lesson for Edrolo. So I thought I'd combine two of my favorite loves, the temper trap and the normal distribution. So hope you enjoyed. Probability and set scores, we know the standard deviations, the normal distribution. Anyway, last lesson on the normal distribution, we're going to be looking at the inverse. So let's get into it. Okay, guys, this lesson is called the inverse normal distribution. It's the last one for the chapter. So let's get stuck in. We're going to be looking at two things today. We're going to be using something called the inverse normal distribution. And we're going to be looking at problems where we aren't actually given the mean and the standard deviation and how we can solve for those. It's mainly going to be using the technology. So have your calculator handy and let's go. Okay, so first of all, we're going to be looking at using the inverse normal distribution. Now, you might remember doing some similar stuff a couple of lessons ago when we were looking at percentiles. And what that was involving was when we were given a probability and we were being asked to solve for one of the terminals under the integral. So this is going to be the same thing, but using the normal distribution. So again, there'll be no actual integration involved. So we're solving problems such as this, where we want to find A such that the probability that X is greater than A or less than A is equal to some figure, and we're solving for the value. So it can again be put in the context of percentiles, depending on the question. But usually we're just told, hey, the probability that X is greater than this amount is 0.38, for example, tell me what A is. Or something like the top 10% of people are greater than what height? And then, you know, we'll work backwards to work out what that value is. So what does it look like? Here's a quick example. We've got a normally distributed random variable, a mean of 16, standard deviation of 2, and I've been asked what's the probability, or we're given the probability of 0.38, and what is this value A, such that the probability to the right of it is 0.38. We're trying to work out this value here. So in our calculator, what we do is we use our inverse normal distribution function. It may look slightly different in the Texas calculator as it does to the ClassPad. In the ClassPad, you need to set a tail setting. You need to set it to the left or the right, whether your probability is to the left or to the right of the value. So because we are doing greater than 8, our tail setting is right. If the tail setting wasn't there, and I think possibly in the other calculator, there isn't a tail setting, it just assumes you're going to the left. So you would just use 1 minus 0.38, which would give you the setting to the left anyway. So that's 0.62. whichever you're using, it's just as straightforward, I hope. So in here, I've set my tail setting to the right, probability of 0.38. I've plugged in my mean and my standard deviation, and it's given me that value of A, 16.61, okay? And then I can answer the question. And then we have a picture. So there's our normal distribution with a mean of 16, and there's my probability 0.38, and you can see that value there is around about 16.61. Okay, let's keep going. Okay, so here's our worked example. Again, we're talking about the caffeine in our company's energy drink. Same random variable C, same mean and the standard deviation that we've been working with, nice and consistent across the lessons. So let's bring it home and do an inverse normal question. It's been determined that the cans with the lowest 5% of caffeine content cannot be sold. So what's the minimum amount of caffeine that a can could contain and still be sold? So what we're looking for here is rather than a probability, we're looking for a caffeine amount. So here's my random variable with a mean of 65, and I want the lowest 5%. So here, this value here, where the probability of a can having even less than that is 0.05. So that's what we're looking for. We're looking for this value here, such that any cans below it are the bottom 5% of cans. So 0.05 is the probability. So to put that in a little bit of working, we know our random variable can be expressed like this. And I know that the probability that C is less than the answer to the question is equal to 0.05, and I'm solving for that A, which I do using the calculator. And what does that look like? Okay, so we're going into the distribution section, the inverse normal CDF, and our tail setting is going to be left here. The probability is 0.05, and we are looking for a standard deviation of 3 and a mean of 65 as before, and then that will give us our answer. So 60.0654 to 2 decimal places, 60.07. So if we round up to 60.07, that would be to 2 decimal places the minimum amount of caffeine that a can could contain and still be sold. The probability that a can being less than 60.07 is 0.05. There you go. Okay, time for you to have a go. Okay, the final thing we're going to look at for this chapter is what do we do when we are not given the mean or the standard deviation or either? And what we do is we use z-scores and we use the information that we know to kind of work backwards to find the mean or the standard deviation or both. So we're usually given a probability and then we can convert that to a z-score and then we use this formula. Okay, that's the basic idea. So let's have a look at the question or this quick example here. So I've been told that X is normally distributed with a mean of 16 and an unknown standard deviation. I don't know what the standard deviation is. However, I know the probability that X is greater than 16.61 is equal to 0.38. I've drawn a diagram here. So what I'm going to do is I want to know 16.61, what is that as a z-score? And I can't work that out based on this information alone because I don't know what the standard deviation is. So I don't know how many standard deviations above the mean 16.61 is. However, for the standard normal distribution, so Z, I could work out the probability, what probability on the standard normal distribution is 0.38. So that's what I'm going to do. So I'm going to use the inverse normal, but on the standard normal distribution. So it would look like this. I've got a mean of 0 and a standard deviation of 1, and I've done the probability to the right is 0.38. So what I've done is I've gotten 0.305. So that is 16.61 as a z-score. In other words, the probability that X is greater than 16.61 is the same thing that the probability that Z is greater than 0.305, etc., etc. So what that means now is that I now know how many standard deviations from the mean 16.61 is. So I can use my z-score formula. So that would mean that 16.61 minus the mean, which is 16, divided by the standard deviation has to equal 0.305. So if I solve that for the standard deviation, I've answered the question. So that's what I do in the calculator, and I get 1.99, or just about 2. You'll remember this example we did before. We had a standard deviation of 2, so I've used the same thing. Okay, so there's our answer. So let's look at another example and try to put this into practice. Okay, so for this question, it's a little bit trickier because what you'll see is we're not given the mean or the standard deviation. We need to work out 2 things. So let's have a look. The time in minutes that students spend using their calculator during a 120-minute exam is said to follow a normal distribution with some variable t. So t is normally distributed. I do not know the mean or the standard deviation. Okay, however, I know that 10% of the time it's less than 60 minutes. 15% of the time, it's more than 90 minutes. So I've been given 2 pieces of information, and hopefully I can use those 2 pieces of information to find my 2 unknowns, which is the mean and standard deviation. So if you've ever done other questions where you had 2 unknowns and 2 bits of information, it usually involved simultaneous equations to answer the question. That's exactly what's going to happen here. Okay, so let's draw a quick picture. So we don't know the mean of our variable. However, we know that 10% of the time is less than 60 minutes. So that's 0.1, and that's 60. And then 0.15, so a little bit bigger area, 0.15 is more than 90. Okay, so before we even get our answer, we should be expecting that our mean should be closer to 90 than it is to 60. So we'll check that right at the end. But let's see what we have here. Let's plug in some more information. So it's known that 10% of the time it's less than 60 minutes. So the probability that t is less than 60 equals 0.1. And the probability that t is greater than 90 is equal to 0.15. Now, just like I did with the previous example or the slide before we got to this question, we're going to work out what 60 and 90 are as z-scores. And we're going to convert them to z-scores by using the inverse normal distribution. So I want to know this 60 and this 90, what does that look like on the standard normal distribution of 0 and 1? So I'm going to work out this number here and this number here. So in other words, z is less than what is equal to 0.1, and z is greater than what is equal to 0.15. Notice I've used a and b there because they're going to be 2 different numbers. Okay. So let's get the calculator out at this point. Okay, so in my calculator, you can see there we've done a left tail for 0.1 and a right tail for 0.15 using a mean of 0 and a standard deviation of 1. And I've got that a value, a, it would be equal to negative 1.28155 ... I'm just writing here that I'm going to lots of decimal places, because remember our final answer needs to be to 3, so I don't want to round off until the end. And then I get that b is 1.0364 ... Okay, so what do I know? I know that 60 is 1.28 standard deviations below the mean, and 90 is just over 1 standard deviation above the mean. So I'm going to use my z-score formula of x minus the mean divided by the standard deviation, and I'm going to plug both of these things into it. So that's where my simultaneous equations will come from. So 60 minus the mean divided by the standard deviation would equal my first z-score, and 90 minus the mean divided by the standard deviation would give me my second z-score. I'm running out of room here. Okay, so I'm going to take those 2 equations and I'm going to put them into my calculator and solve them simultaneously. However you like to solve simultaneous equations in your calculator. I'm using x and y here instead of the mean and the standard deviation. Just remember which one you made x and which one you made y. But it should be obvious from the answer. So there's my answer. X is 76.586 and y is 12.942. So x was the mean. So the mean is, to 3 decimal places, 76.586, and the standard deviation is 12.942. You'll remember before we were saying we're expecting the mean to be closer to 90 than it is 60, which it is just slightly. 76 is a bit closer to 90 than it is to 60. So there you have it. Quite a complicated question and quite a lot of steps there, but they are all kind of like that. Okay, the questions are all quite similar. Just note that if you're only looking for the mean or the standard deviation, you'll only be given one piece of information because you won't need the simultaneous equations. And of course, if you need both, you'll be given the 2 bits and you can follow it through like this. Okay, time for you to have a go. Okay, so to sum up the lesson, we were talking about the inverse normal distribution, similar to when we were looking at percentiles, when we're trying to solve for one of our terminals on the integral, where we're trying to find a value rather than a probability. That's the same thing here. So we're using the inverse normal distribution to work out some value where x is greater than that value is equal to whatever probability we're given, okay? We also looked at problems where we don't know the mean or the standard deviation, where we're employing z-scores here and the standard normal distribution to get those z-scores and then plug it into our formula, x minus mu divided by the standard deviation to get our mean or whatever, okay? Hopefully it made sense to you. Chapter checks now, and that is the end of my work for you on Edrolo. It's been a wonderful 2 years being with you. Shout out to Dougie from the Temper Trap. I'm really sorry I butchered your song. You're never going to hear it in the same way again, but it is a beautiful song, Sweet Disposition. So chuck it on your Spotify and relax knowing that you are done with continuous random variables. And you've got 1 chapter to go in methods. And I hope you do really, really well this year. And all the best. See you later.